I'm going to walk you through some of your homework to help tie in what we've been talking about in class with these polarity of bonds. And we're focusing now on covalent compounds, which share electrons. But part of the reason why atoms will combine covalently rather than ionically goes back to the concept of electronegativity. And so we have some atoms that are more likely to gain electrons, and we have some that are more likely to give away, like this one right here. It seems very, very happy to give away this electron. And this other atom is going to be the one that accepts it. And when it does that, because it loses that negative charge electron here, which goes over here, this is now positively charged, and this atom here ends up being negatively charged, and those opposite charges attract. And the reason that happens is because we have this atom here that is very, very electronegative. Gimme, gimme, gimme electrons. In comparison to this one, which doesn't really care whether or not it has it. In fact, it's better without it because then it can form its octet below that valence shell. And so those are ionic bonds. And what we're going to be looking at here is the difference between the electronegativities and how that relates to their pull of electrons individually. And then we're also going to look at covalent compounds. Here in this picture, it seems like we have even sharing of these two electrons. So those two electrons will go in between those two atoms, and that would be a non-polar covalent bond, which means there's equal sharing. But as we'll see, there isn't always equal sharing, and if you read your comic book Polar Bear homework, then you already know part of the story. If I'm unraveling this introductory paragraph here, I'm seeing that they're describing a tug of war between or over valence electrons, and the type of bond that forms depends on the outcome of that tug of war, and that outcome is determined by the strengths of forces, which is measured by something called electronegativity. And it's that electronegativity which will tell us if it's greater than a value or equal to 1.7, that's ionic. If the value is close to 0, then we have something that is going to be nonpolar because they are sharing equally. There's almost no difference between their electronegativity poles. A higher value for electronegativity difference is going to give us polar bonds. As we look at the first example that they give us, we'll notice that they have the low electronegativity value first, and then the high electronegativity value will be next. And that tends to be metals for the lower electronegativity because they tend to give away electrons, and it tends to be nonmetals that have the higher electronegativity. So we're looking at sodium and bromine, and if we look at sodium and bromine at our example table here, we have a 0.9 for the sodium, and I don't know if this is a typo here, but it says 3.0 for bromine, and on here, bromine says 2.8. But either way, what we're going to do is we're going to subtract the low from the high, and the electronegativity difference is what we're looking at. And so even if that was, let's say, 2.8, the difference there would be 1.9. That's still something that is, it is greater than 1.7. So either way, that's something that's going to be ionic. If we look at the next example, we have hydrogen and chlorine. Hydrogen has an electronegativity value of 2.1. The chlorine has an electronegativity value, that one is 3.0. The difference between those two, if we subtract the 2.1 from the 3.0, you get 0.9. And that value, it is less than 1.7. It's definitely not about 0. So this is not equal sharing of the electrons. Therefore, this is a polar covalent bond. Okay, don't be lazy and just write polar. It is polar covalent. And then the other type would be nonpolar covalent. So pause the video and do the next two, and then we'll check the answers. Pause the video. And here are the answers to those two particular problems. I hope you're getting the hang of it. Go ahead and finish up the last 5 that are in this column, and when you're done, turn the paper over and let's do the back side of the homework. I'm going to go ahead and leave this table enlarged a little bit here so that you can read the values more easily for those last few. Part 2 of tonight's homework involves drawing Lewis structures and using them to predict whether or not a compound will be polar. So we've been practicing polar bonds up to this point, and now we're going to look at the molecule as a whole and tell whether or not it's polar. And we're going to do that using our amazing Lewis dot structures. As we read to unravel the introductory paragraph, we have a lot of the same information that we did on the first side, but now since we're talking about molecules, we have new information here. So I would highlight this or underline it. Molecules with polar bonds distributed symmetrically are nonpolar. Asymmetrical molecules with polar bonds are polar. For example, water is a polar compound. An imaginary line can be drawn through the water molecules, separating the positive pole from the negative pole. And so that's what that looks like here in the picture. If we took a water molecule, we would actually be able to bisect that molecule, and we would get one half that was very weakly electronegative and one side that was very strongly electronegative. So we would have an unequal balance of where the electrons are. So that's what makes that polar. What's interesting though is if we look at water from different perspectives, if we looked at cutting down water through the middle, we do actually have 2 symmetrical sides to it. But remember that molecules are constantly moving and they don't just stay in one position. They're constantly moving around. And so we have to look at all angles of the molecule. And since there is, if we cut it in half this way, since there is a positive end and a negative end, this is asymmetrical, therefore water is a polar compound. If we were to look at what a nonpolar compound looks like, if we cut down the center here, we'll see that the left and the right side have an equal distribution of where the positive and negative charges are. So because there's no difference between those two, that's nonpolar. And then likewise, if we horizontally bisect that, and we'll see that this side here is exactly just a mirror image of this here. So again, that's going to make it nonpolar because there's not a difference in the charges on either side. Okay, now to work some of the problems. Starting with HCl, we saw that on the other side of this paper, that if we looked at the electronegativity values, that comes out to have a polar type of bond. That means that the hydrogen and the chlorine do not equally share the electrons. So what does the electron dot diagram look like? Well, we practiced this in class. We find the sum of the valence electrons of all of the elements present. Hydrogen will have 1. Chlorine has 7. The sum of that is 8. So as we draw what this structure is going to look like, we have a hydrogen. We have a chlorine. Step 2 says that we're going to put a dashed line to represent a bonding pair between those two. And then we distribute any extra electrons around the more electronegative atom. So this was 2 electrons here, which means that we have 6 more to distribute. 1, 2, 3, 4, 5, 6. All right, so that's our electron dot diagram. Hydrogen and chlorine are not the same element, so they are not going to share equally. The more electronegative atom is where the electrons are going to move towards, which means we're going to have a positive, partial positive charge on the less electronegative. So this right here tells us that the type of compound it is, it's a polar compound. So it has a polar bond in it, and it is a polar compound. Right, if we look at methane, CH4, what type of bond is this? Well, we can look back at our values and we can see that there's enough of an electronegative difference. These are going to be polar. So the type of bond is polar. Now to draw the electron dot diagram. The carbon is going to be in the middle because I know that the hydrogen, I can only have one bond for each hydrogen because it is such a small atom. So it's going to have to be on the outside of my central atom. We need to account for all of the valence electrons. Carbon will have 4 because it's in group 4A. Hydrogen has 1, but there are 4 hydrogens, so that's 4 total. So we should have 8 electrons within this electron dot diagram to account for. I have 4 hydrogens, so let me just go ahead and surround my carbon with those. And so the next thing I do is I create bonds in between the central atom and the surrounding atoms. I make sure that my central atom has an octet. So here's 1, 2, 3, 4, 5, 6, 7, 8. Each hydrogen is stable, it's happy, because it's a small atom, so it actually only needs a duet of electrons. Carbon has its octet. So if we look at the individual bonds, if we're looking at where the electrons are going, carbon is the more electronegative atom, so we're actually going to have a pull going this way. We're going to have a partial positive from the hydrogen, and the electrons are going to be moving towards the carbon. So the bond is polar between the carbon and the hydrogen. However, if we look at the symmetry, if we look all around at each side, whether we cut it in half this way or cut it in half this way, we would have the same charge on the outside. So this is actually going to be a nonpolar compound. So there are polar bonds within the compound, but it's a nonpolar compound. Let's do another one. Go ahead and pause the video and try to work through chlorine, and then let's check our answers with what we have. Chlorine, I think, was a little bit easy because we can tell it's one of our 7 diatomic elements, and because it's the same atom, then it's going to share equally. It's going to have the same electronegative pull on the electrons. So the bond is nonpolar, and because the bond is nonpolar, then the molecule is nonpolar here as well. The potassium bromide on the next example, this one's kind of tricky because it's actually an ionic compound. So let's go ahead and do this one. I'll do this one together with you. So this is ionic, and I can tell that because I have a metal and a nonmetal, and I can double check. I can go back and look at my electronegative values, and I will see that there's a great enough difference that that bromine is just going to rip that extra electron off of the potassium, so it's going to be an ionic compound. So when we draw our structures for ionic compounds, remember that the Lewis dot structures show that we should have a full valence shell, and that's because potassium lost its 1 valence electron. Right? We started off with, it was in group 1A, so it had 1 valence electron, but then as it lost it, it went down to the lower energy level. Okay. And bromide, on the other hand, will actually, it starts off with 7, and it will accept an electron. There's the one it accepts, and that gives it a negative charge, and that's what brings it together. Okay, so there's no sharing whatsoever, not covalent at all. This is ionic, so ionic bonds result in an ionic compound. All right, so go ahead and pause the video one more time. Try NH3 ammonia, and then check your answer. And here's our answer for ammonia. It is a polar compound with polar bonds. We can look at our electronegativity values here, but I also just know that nitrogen is a larger atom than hydrogen. It has many more protons than hydrogen does, so there's going to be a pull for those electrons to move towards the nitrogen. So there's going to be a partial positive end wherever we see the hydrogens. There we go. And then again, if we look symmetrically at this, if we were to bisect this, if we were to try and cut it in half, we would see that this half of the compound has partial positives, and this here has this free-floating set of electrons, and then the electrons are moving this way. So that makes it a polar compound. So go ahead and finish the rest of those notes, and we will check them in class and move on.